Hello everyone, this is a quick video on how to do problem number 4 in the chapter 10 homework. And in this particular problem, we've got a 0.43 molar solution of the monosodium salt of mercaptoacetic acid. Okay, so what the heck is that? Well, we look up the structure in the appendix and we see that in its fully protonated form, the mercaptoacetic acid itself, this part, before we do the monosodium salt. So the fully protonated form is going to be an H2A formula and charge. So it's electrically neutral H2A. It's diprotic. So now from this piece of information, we can quickly make the pKa diagram. We've got a pKa at 3.64. We've got a pKa at 10.61. And then we put our most acidic form, our amphoteric intermediate, our most basic deprotonated form in there. And now we can think about what is the monosodium salt. Well, we can see that in H2A, mercaptoacetic acid, we could replace one or both of the protons. And so the monosodium salt is going to be, monosodium salt of this guy is going to be right here. So that's going to be the form. So now we have 0.43 molar solution of the intermediate HA minus. So we can think about that now. 0.43 molar HA minus. And knowing that, we can immediately figure out, I wrote an A there if you can't read that, an A, we can figure out our pH from halfway between the two pKa's, because that's the way you start for any intermediate problem. So we got 1/2 pKa 1 plus pKa 2. And when we do the math, I get 7.125. And we'll, at the very end of the day, we're going to round that to 7.13. But for now, we're going to keep it as 7.125 because we're going to find from that the H plus concentration. And we get that value 7.50 times 10 to the minus 8th molar. And we'll use that number in some subsequent calculations. Okay. Sort of step B in this intermediate process, after we've figured out the pH, that's absolutely step 1. Don't go any farther until you do that first. Then we're going to make the assumption that will be wrong, or it may be a good assumption. We'll find out at the end. We're going to assume that the concentration of our intermediate is the formal concentration. And at the very end, we'll see what the concentrations of the fully deprotonated form and the fully protonated form are. And we're going to subtract those from the formal concentration. And we'll find out if, in fact, this assumption was good or if we have to have a slightly corrected value at the very end. All right, then when we think about the actual chemical reactions that will determine the concentrations of all three of the species, they are these. So first dissociation of the fully protonated form makes the intermediate. And the Ka that describes that you can look up, but it's going to correspond with that pKa, 2.3 times 10 to the minus 4th. And then the second dissociation controls the production of the fully deprotonated stuff. Through Ka2. Okay, so we've got this information and we're going to keep referring back to this page as I go on to the next page to do the actual calculation. So we're going to start with reaction 1, and we're going to use Ka1 and the expression products of reactants along with our assumption that HA is 0.43, our knowledge that H plus is 7.5 times 10 to the minus 8th, and from the expression, we're going to be able to calculate H2A. And we'll do a similar kind of thing with the second reaction and the expression for Ka2. So as we do that, so from that first acid dissociation reaction, we get this for Ka1. And we know that this guy from the previous page was 7.5 times 10 to the minus 8th molar. And our concentration of HA, we were making the assumption is the formal concentration, 0.43. We know the value for Ka, and we plug that in. And then we can easily calculate the concentration of H2A by doing a little bit of simple algebra. And that value that I got was 1.4 times 10 to the minus 4th molar. From that second dissociation, so through Ka2, we can see the H plus concentration we know. We know the HA minus concentration, which will be in the denominator. We know Ka, and then we can calculate the concentration of A2 minus. So from that equation, we end up with this. Ka2 is concentration of A2 minus times H plus all over the concentration of HA minus. And then we know, like I said, the value for Ka2 from the previous page. We know H plus. We know that we're assuming this value is 0.43. And then we have everything plugged in. We can calculate A2 minus. And when I do that, I get a number very close to, once again, 1.4 times 10 to the minus 4th. Okay, so we've got the concentrations of the fully deprotonated form and the fully protonated form calculated. And now we can correct our, if necessary, correct our assumption that the concentration of the intermediate is really 0.43. So now we're going to use the mass balance, which is that the formal concentration, the total sum of all the concentrations of all the species will actually be 0.43. Like this. And so we're going to plug in the actual values that we got for H2A and for A2 minus. And we have our value for the formal concentration, and by difference, we should be able to get HA minus. So basically, it looks like this: 0.43 minus 1.4 times 10 to the minus 4th for the H2A minus 1.4 times 10 to the minus 4th for the A2 minus gives us our concentration corrected for HA minus, and we do the math, and I got 0.4297, which is to 2 sig figs 0.43. So our assumption that the concentration of the amphoteric intermediate that we started with was 0.43 was a good assumption. And so now we can summarize our final results. We know our pH, which was one of the things we wanted to calculate, was 7.13. Concentration of the fully protonated H2A, 1.4 times 10 to the minus 4th. Concentration of the intermediate, 0.43. And the concentration of the deprotonated A2 minus, that's supposed to be a 2 there, was 1.4 times 10 to the minus 4th.